In today's lesson, we're going to learn about something called the parent functions. In our course, in order to learn the proper techniques of transforming functions, there's going to be 4 different functions that we're going to focus on that we commonly see in mathematics. And these are going to be what we call our parent functions. Here's all 4 of them listed below. We have the quadratic function, which we've seen before previously in grade 10 and already this year. And here are 3 new functions that we're going to see. The first one's called the radical function. It just looks like a square root of x. The next one's called the reciprocal function, or 1 over x. We remember reciprocals back when we were talking about exponent rules. And the last one here is something that you wouldn't have seen before, and it's called the absolute value function. And this is what the notation looks like right here. It looks like 2 bars with an x in between it. Let's talk about what absolute value means. When we want to take the absolute value of a number, all we're really saying is, what is the distance that number is from 0? So it could be a positive distance or a negative distance, but whenever we talk about distance, distance is always as a positive number. So for instance, the absolute value of the number 6, when we write it in bars like that, well, the distance that 6 is away from 0 is simply 6. Whereas the absolute value of negative 4, well, the distance negative 4 is away from 0 is 4. Notice how positive 6, or the absolute value of positive 6, turned into or remained positive 6, but the absolute value of negative 4 turned into positive 4. Essentially, we can think of it as anything that we write in the absolute value signs, no matter what number it is, positive or negative, will equal the same number, but the positive version of it. So anything positive will stay positive, anything negative will turn positive. So we'll see that function a little later on. But let's start with graphing the quadratic function. So here's our quadratic function, f at x equals x squared. For each of these parent functions, we're going to look at 4 things. The first thing is what the graph of each of these functions look like. Now remember, these are the basic functions. These functions have no transformations on them. They're just the normal functions you would see without any stretches, compressions, translations, or reflections. So here we have our standard quadratic function, f at x equals x squared. And if I created a table of values where the x values range from -2 all the way to +2, we generate these points that are already labeled on our graph. And we could fit a curve through those 5 points, and here this would be our graph. So the graph is the first thing we're going to look at for each of these. The next thing we're going to look at are all of the key points that are associated with this parent function. So for each parent function, there's going to be points that we can use, and if we remember what they are, we'll use those points with the RST chart and find an easy way to graph any reflections, stretches or compressions, or translations. The last thing we're going to look at are what the domain and the range are for each of our parent functions. So let's start with the quadratic function, which we've already seen many times before. We already see the graph, and our 5 key points are labeled on this graph. So here are the 5 key points. -2, 4, -1, 1, 0, 0, which is our vertex, 1, 1, and 2, 4. Again, we're going to use these points as the key points when we want to graph or we want to take or create our translations. So we have to remember what these points are. For all 4 of these parent functions, there's going to be key points that you need to memorize. They'll be easy the more you work with them, but you will need to memorize these. So -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Finally, we'll look at our domain and range. So we can see that for our parabola function, the x values will exist everywhere in the real number system. Each side here goes on forever, and eventually every x value will be hit. So our domain we can define as just x, er, or x, or all the values of x are elements of the real number system. Our range for this parabola, or our standard parabola, exists that all the y values are members of the real number system where y has to be greater or equal to 0, since that's where our vertex is. So our range is going to look like YER such that all the values of y have to be greater or equal to 0. If we think about any parabola, notice how the domain will always be XER. There's no other way, or there's no other possibility for the domain. The range, on the other hand, will always be dependent on where the vertex is. If the parabola opens upwards, then all the y values will be greater or equal to the y value of the vertex. And if the parabola opens downwards, then all of the y values will be less than or equal to the y value at the vertex. And there you have it, your first parent function, the quadratic function, with its graph, its 5 key points, and its domain and its range. Have you memorized it yet? The next parent function that we're going to look at is called the radical function, or f at x equals the square root of x. Now when we talk about the square root of x, we have previously shown that when we take the square root of a number, we always want to consider the positive and the negative solutions to it. However, when we talk about the radical function, we only take or consider the positive version of the square root of x. So, if x is a negative number, this function does not exist. Look at our graph and you can see that the x values start at 0, 0, because we can't have any x values that are negative. It also goes to show that if all the x values are positive, then all the y values will be positive too, because when you take the square root of any number, you still have the same positive sign. So here we're going to have 3 key points only for the radical function. The first one's easy at 0, 0. Most of these parent functions have a key point at 0, 0. The next one's going to be at the point 1, 1. It makes sense that when we plug 1 in for where x is, our y value, or f at x, is going to equal 1. The square root of 1 is 1. Then we're going to skip 2 and 3 because 2 and 3 aren't perfect squares. So our next key point is going to be involved when x equals 4. Well, when x equals 4, y equals 2. So we have this key point here, and we have this key point right here. So 4 and 2. Those are going to be the 3 main key points for our radical function, 0, 0, 1, 1, and 4, 2. But sometimes it helps just to have a fourth one. And if we were to create a fourth one, I'd probably use the point 9, 3, because 9 is the next perfect square. So when x is 9, y, or f at x, is going to equal 3. And so really, there are 4 key points we can remember for the radical function. Our domain exists that for all the x values that exist, they're each going to be elements of the real number system, but of course we can never have a negative square root, or so our x's are going to be limited to being greater or equal to 0. It's okay that an x value can be 0 because we can still take the square root of 0, which is equal to 0. Our range then is going to be sort of the same as what our domain was for x. All of our y values will still exist on the real number system, but all the y values will have to be greater or equal to 0. There's no way that any y values can be negative. And so there you have it. Our graph, our 4 key points, and our domain and range for the radical function. Our third parent function that we're going to look at is called the reciprocal function. And this one tends to be the most difficult one to graph. The equation for it here is f at x equals 1 over x. It seems simple enough, but look at this weird graph. There's actually 2 curves associated with this function. One of them in the positive x and y quadrant, and one of them in the negative x and y quadrant. Remember, we call this quadrant 1 up here, and we call this quadrant 3 down here. Maybe you didn't know that, but now you do. Quadrant 1, quadrant 3. Just so you know, quadrant 2 is up here and quadrant 4 is over here. But we're going to get to that in the next unit. So let's take a look at how this function works. Notice whatever value you put in for x, we always get the reciprocal, or 1 over that number. So if I take my first key point is at 1, where x value is 1, notice how y, or f at x, will also be 1, because 1 divided by 1 is 1. So that's a really easy key point to know, 1, 1. I don't want to use 0 for x, because 1 divided by 0 we know is undefined. We'll get to that in a second. But let's look at another point. What happens if x is 2? Well, when x is 2, y, or f at x, is going to equal 1 over 2, or half. So that looks like another key point right there. 2 and half. Well, if I plotted that, that would be right here. If I continue in this trend and I put x is 3 and x is 4, I'm just going to keep getting fractions of 1 over 3 and 1 over 4 and 1 over 5 and so on. And notice how then I would just keep plotting points on this downward part of this curve. But I still want to represent the upward part too. So I'm going to plot this point right here. That's when x is half. So when x is half, we have 1 divided by 1 half. And we know that when we divide by a fraction, like 1 half, it's the same thing as flipping and multiplying. So 1 divided by 1 half is the same thing as me writing 1 times the reciprocal, which is 2 over 1, or is just equal to 2. And that's how we get this point right here, half and y would equal 2. So there we have 3 key points that we can use for the reciprocal function when x and y are all positive numbers. But that's just one of the 2 curves that are associated with this function. There's also the ones where they're all negative. So those key points are going to exist too. So if x equals negative 1, well, 1 divided by negative 1, well, that's equal to negative 1 right here. So y would equal negative 1. Again, when x is equal to negative 2, 1 divided by negative 2 is negative 1 half. And last but not least, when x is equal to negative 1 half, we get 1 divided by negative 1 half, which is just negative 2. And so that's this point right here, and this point right here. And so you can see we have 6 different key points that are truly used to define this function, the reciprocal function. All 6 of these points are ones that you're going to need to memorize. You can't just use the positive ones, and you can't just use the negative ones. You need to use all 6. Because when we want to accurately plot these transformations, some of these are going to be transformed a little differently than the negative ones, or maybe the negative ones will be transformed a little differently than the positive ones. So we need to use all 6. Now, what has happened here when x is equal to 0? Notice how the curve gets ever so close to 0, but will never actually touch it. Well, we have a special word for this type of line, and I'm just going to draw a little green line here to help sort of visualize where this is. There's one going on this way too. Notice how the curve almost touches the x-axis but never quite does. Because no matter what number we put in for x, no matter how far we go, like if x was 100, well, y would equal 1 over 100. Or if x was equal to 10,000, y would equal 1 over 10,000. It would get closer and closer to 0, but will never actually touch it. There's no way that we could make the y value equal to 0. Just like there's no way that x could equal 0, because I would get an undefined function. So when we have a curve that gets ever so close to this line, but never actually touches it, we call this line an asymptote. Spell it out for you because it doesn't quite spell the same way you read it. An asymptote. There's a P in there and a T in there. You can bet that you're going to need to spell this on some quiz or test in the future, so make sure you spell it correctly. Both of these green dotted lines are asymptotes. And asymptotes have equations just like vertical or horizontal lines would. So the equation of this asymptote right here, because it goes through the value x equals 0, is simply x equals 0. And the equation of this horizontal asymptote, because it goes through the point y equals 0, well, that's easy to say also, y equals 0. There's going to come times when you're going to need to figure out what the asymptotes are of a function, and you'll have to give the correct equation for them. So just remember, if you have a vertical asymptote, whatever x value that vertical line goes through, that's your equation. In this case, x equals 0. And if you have a horizontal asymptote, whatever y value that goes through is the equation for that asymptote. So y equals 0. So we have 6 key points, we have 2 curves on a graph, we have 2 asymptotes. My oh my, this is one of the more difficult ones to graph. Well, let's talk about what the domain and the range are. So if we think about all the possible x values that can exist, notice how our curve goes on forever in the x direction going this way, but stops right before x gets to 0. And then immediately after x hits 0, so going into the negative side, it starts back up again, and then goes along here and continues on forever. So really, all the x values, again, are elements of the real number system. But the only restriction we have here is that x can't be 0, because that's on our asymptote. So x is equal, or xer, but x cannot equal, or does not equal, 0. When we do the domain and the range for the reciprocal function, our little stipulation here is always going to be that x or y can't equal whatever the asymptote is. So again, for our range, all the y values will exist, because this goes on forever upwards, and this curve goes on forever downwards, except for when y is at 0, because the curve never actually touches y at 0. So yer and y cannot equal 0. So there you have it. 6 key points that we need to memorize. 1, 1, 2, half, and half 2, and -1, -1, -2, -half, and -half, -2. It's like there's only 3 key points, but the same set is repeated, but all negative. And our domain and range are xer, where x can't equal 0, and yer, where y can't equal 0. Don't forget about the asymptotes, and make sure you spell it correctly. Our final parent function is called the absolute value function. And I've already explained what absolute value means, but just to repeat it, remember, any number you put in the absolute value signs just turns out to be the positive of that number. So if you put in 4 in there, it'll still stay as 4. But if you put in -3, it'll come out as +3. So here's our graph. We still have a point 0, 0 here right in the middle, which we can use as one of our key points. And we're also going to use the point when x is 1, well, y will equal 1, because the absolute value of 1 is 1. And when x is 2, y will equal 2, because the absolute value of 2 is 2. So those are 3 easy key points, here and here. And then going the other direction, when x is -1, well, the absolute value of -1 is +1. And when x is -2, well, the absolute value of -2 is +2. And so this gives us the 5 key points we can use for the absolute value function. This is very similar to a quadratic function, but remember, a quadratic function is curved and goes upwards at a much faster rate, because you're squaring the numbers, not just taking the positive of the numbers. So this is more like a V-shaped curve, whereas a quadratic function is more of a U-shaped curve. Our domain and range for this one, though, is very similar to the quadratic, where our domain is always going to be xer. You can put whatever number you want in for x and find the absolute value of it. And our range is just yer. But again, our y values will never be less than 0, because our absolute value turns everything positive. So y has to be greater or equal to 0. Now, that's not to say that this function will never have y values that are less than 0, because remember, this is just the parent function. We're going to be taking these functions and we're going to be putting some transformations on them, like stretching them, compressing them, translating them up, down, left, right, or even reflecting them over the x-axis or the y-axis. So it is possible for an absolute value function to have a range where y values are less than 0, but not the parent function. The parent function will always have y values greater or equal to 0. And there you have it, our 4 parent functions: the quadratic function, the radical function, the reciprocal function, and the absolute value function. Remember, you need to memorize what the graphs look like, what the key points are, and what the domain and the range are. And for the reciprocal function, you need to know where the asymptotes are. Knowing this is very important, and if you don't remember what the key points are for any of these 4 functions, or what the graphs look like, then you're going to have a very difficult time graphing any of their transformations. So your job today is to make sure that you have all 4 of these key points, graphs, and domain and ranges memorized for these 4 parent functions. And then during the next lesson, we're going to learn how to transform them.